Good afternoon, ladies and gentlemen. Welcome to another exciting episode of Dave Does Math from Home. On today's episode of Dave Does Math from Home, we are talking about derivatives. We are finally finished with Chapter 2. We are done learning what limits are and how they work and what they mean. And it is time now to put that knowledge to good use. We're going to actually use limits to do some real calculus. It begins. Before we get into calculus, I want to review some of the things that we've recently said about slopes. Because the first really big idea about calculus is fundamentally tied to the concept of a slope. Slope, as we know it, slope is a characteristic of straight lines. Something has to be straight in order for it to have a slope. That slope is the constant rate of change of that straightness. The idea of slope is difficult to apply to things that are curvy or wiggly. Basically, if you think about all of the different families of functions that we've talked about, polynomials, trig functions, exponentials, logarithms, rational functions, everything. All of these functions are curvy and wiggly in various places. They're very rarely straight. Some of them look straight sometimes. They're almost never actually perfectly straight. Perfectly actually straight is something that happens with lines, which are first degree polynomials, but those are boring. We want to talk about things that wiggle. And we want to talk about the rate of change of things that wiggle. And slope is the closest we can get to that right now. Slope, we said, is the constant rate of change for things that are straight. Things that are not straight, things that wiggle, they do not have a constant rate of change, but we can still talk about their rates of change. We just have to switch, I don't want to use the word change too much, we have to switch the ways that we're talking about this. So let's, for now, talk about an average rate of change. The average rate of change basically means we're going to use this idea of slope and we're going to apply it to things that are not straight. Slope is m, it's change in y over change in x. It is y2 minus y1 over x2 minus x1. And if you're doing this on a straight line, it doesn't matter which point you choose. If you're doing this on something curved, like let's talk about the parabola y equals x squared plus 1. This is a standard x squared parabola, just lifted up, vertically shifted up 1 unit. It is very clearly not straight. It's doing a curve. But I want to talk about the average rate of change. The idea that we're going to use to apply slope to this thing is to pick 2 points on it and find the slope between those 2 points. So we might start off with something like x equals 1, and way over here we'll go with x equals 4. It's not going to match this slope, this curve perfectly. It's going to be we can get a straight line between these 2 points on the graph. And we can find the slope of that straight line. And depending on which 2 points you choose, you're going to end up with different lines. The 2 points I choose are going to have a fairly steep slope going up. If we had chosen these 2 points, it would have been horizontal. If we had chosen a point here and a point here, we would get something negative. So there isn't a constant rate of change here, but we can talk about the average rate of change just by picking 2 points. We'll do x1 and x equals 4. If these are the 2 points I'm going to use, I already have x2 and x1. That'll be 4 minus 1. If we're using this as our slope formula, to get y2 and y1, we're going to have to plug f into this function. So when we plug in 1, we should get that y equals 2. And when we plug in 4, we should get that y equals 17. 4 squared is 16 plus 1. So I'll do these two differences and then subtract them. I should get 15 over 3 is 5. So the average rate of change of this curvy wiggle line between x equals 1 and x equals 4 is 5, which corresponds to what we can see on this graph here. We were expecting a steep positive number. 5 is a pretty steep positive number. We got that. So this is how we can get average rates of change. Here's the problem. I'm not interested in average rates of change. Average rates of change are just, they're sort of pretend. Like, this isn't what the function is doing. It's like, it's the slope of a straight line that crosses the function a couple times, but it's not really what the function is doing in between. It's possible to get average rates of change that kind of don't make any sense. Like if you pick x equals -1 and x equals 1, you just get a flat line. And like a slope of 0 is not very representative of what this function is doing. So I think that we can do better. And that's where the idea of difference quotients come in. Average rates of change are fundamentally about the slope of the line between two points, which is why we're still using this old busted slope formula that is about 2 points. x1, y1 is the first point, x2, y2 is the second point. Average rates of change are about the slope between these 2 points, and that is old news. We've been doing slope calculations in algebra for years. I do not want to start doing them again. What I'm really, really interested in is not the slope between 2 points. What I really want is the slope at 1 point. This is what I want. So how are we going to do that? I spoke too soon a little while ago. This is where the idea of difference quotients comes in. We talked a little bit in chapter 1 about difference quotients, so let's talk some more about them now. We said a while ago that a difference quotient is what happens when you switch around the equation for a slope so that instead of being about 2 different points, it foregrounds one of those points. So the difference quotient is about f of a plus h minus f of a all over h. And this is what happens. F of a, let's start with, maybe we should start with this. A is the point that I'm really, really interested in. Or I should say A is the x value that I'm really, really interested in. And instead of having a second value that I'm going to look at the slope between these 2 points, I'm just going to sort of artificially create a second value based on A, using h as some distance away from the point I care about. So A is the x value that I care about, h is some distance away from it, which gives me my second x value, which is a plus h. And if you want a slope, a second point behind the first one, then you can just make h negative. It doesn't matter. So this is sort of my artificially created second x value. This is y1, it's f of a. This is y2, it's f of a plus h. And if you do the slope calculation using these guys, the a's on the bottom cancel. That just leaves you with an h on the bottom. And we've done a few of these in chapter 1. And this is now going to really highlight the idea of a slope at the point A and a little distance away from A as well. So if I try to use, if I go back to my original function, f of x equals x squared plus 1, I'm going to go through sort of the same slope calculation I did earlier to get the average rate of change using the difference quotient instead of a slope, so that we can sort of see how they're connected. If I want to end up with the same slope, I need to essentially be using the same points. In the first example, I used x equals 1, so that'll be my A. And I used h was 3, because my second point was 4, which created an h value of 3. I'm going to write that down for now. So this is what gives me my first point of 1 and my second point of 4. But I'm not going to actually plug the h in until the very end, so we can see what this looks like as a difference quotient. So the difference quotient is going to be f of a plus h, so 1 plus h squared plus 1. This is what f does to things. Squares something and adds 1. Minus f of a is a squared plus 1. I'm sorry, a is 1. Let's do a equals 1. Over h. So when I simplify this, I will get 1 squared plus 2h plus h squared plus 1 minus 1 squared minus 1. So the 1 squareds will cancel, the 1's will cancel, all this is still over h. All that's left is 2h plus h squared over h, which is 2 plus h. So 2 plus h is the difference quotient using h's, and fixing a is equal to 1. So if I want the difference quotient, or the slope between 1 and 4, I would have to set h equal to 3, and I would get 5, just like I did on the other one. The advantage to doing it this way is I can now set h to be whatever I want. So in my graph, I have this graph. Here is x equals 1. When I went out to x equals 4, this gave me a slope of 5 at the point, I guess I should bring it in a little bit. When x equals 4, I had a slope of 5 between 1, 2, and 5, and 4, 17. But because I have this, based on this a equals 1 point, I can very easily now find the slope between this and like pretty much any other number. So if I wanted to bring it into like x equals 3, if I want x equals 3, that means that its distance away from a is 2. And I can see very easily that that slope would be 4. A little less than 5. If I wanted to do h equals -1 to come back here to x equals 0 on the back, that would give me a slope of 1. I can just plug h equals -1 into this and get that slope as well. From the point a equals 1, I can use this difference quotient I found to find the slope between this and any other number. So that's kind of handy. But here's where it gets really, really interesting. What if I didn't want to use a separate point? This is still fundamentally about the slope between two different points, x equals 1 and x equals 4, or x equals 3, or x equals -1. I said earlier that what I really, really wanted here was the slope at one point. So what happens happens if h equals 0? If h equals 0, in this example I have down here, I'm not talking about the point a equals 1 and then a separate point that's far away from that. I only really have one point now. It's just a equals 1. Which is what I wanted. What happens mathematically? Here, if h equals 0, we got big problems. H is in the denominator. It's not going to work. We're pretty boned. This is no good. So, h can't equal 0. It's just not going to work for us. Unless we cheat. What if we take the limit as h approaches 0? Plan A is always going to fail us because we have this h in the denominator. It's never going to work out. Plan B is going to work out really, really well every single time. So here's what's going on graphically. At x equals 1, instead of looking at the slope between 2 points, we're looking at the slope at the 1 point. And when you set h equal to 0 in the limit, it can't actually be equal to 0 because that's bad, but we can take the limit as h goes to 0 of this difference quotient to get this slope. This is the slope at 1 point. And it's called a derivative. A couple other quick pieces of vocabulary before I cut this video short and start the next one. If you're going between 2 points, that is called a secant line, and the average rate of change is the same as the slope of the secant line. I'm not writing this down because I have to talk real fast. This video is about to cut itself. My memory card is formatted poorly. So between 2 points is called a secant. At 1 point is called a tangent, and the derivative is the slope of the tangent line. These words, secant and tangent, have nothing to do with the trig functions, which is part of why I hate them so much, and you won't hear me say them very often, but that's what they are. Now you know. Stay tuned. Part 2 is coming.